Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the strangest questions ever asked by human curiosity. What is nothing? It sounds simple at first, almost too simple. After all, nothing is something we think we understand immediately. If someone asks you to imagine nothing, you might picture a dark, empty room, or perhaps a silent stretch of space between distant stars, a place without sound, without objects, without movement. But here is the first gentle twist in tonight's story. Darkness is still something. Silence is still something. Even empty space is still something. True nothing, the absolute absence of everything, is far more difficult to imagine than it first appears. But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into nothing together. And if your mind begins to wander, that's perfectly fine. Let it drift. We will still be here, quietly unfolding the story. Imagine a simple wooden box sitting on a table. Inside the box there are books, stones, and perhaps a few scattered coins. To create nothing, you begin removing them one by one. The books come out, then the stones, then the coins. Soon the box is empty. But something is still there. The box is filled with air. Invisible perhaps, but very much present. So you remove the air as well. In a laboratory, this can be done using pumps that slowly draw the air away until almost none remains. What you now have is called a vacuum, a space with extremely little matter inside it. At first glance, that might seem like the closest thing to nothing, but even this empty space still contains something. There is still space itself, the quiet stage upon which the universe exists. There are still invisible fields that physicists believe fill every corner of reality. There are still faint traces of energy flickering quietly in the background of existence. So once again, the idea of nothing slips gently through our fingers. Part of the difficulty comes from the way our minds evolved. Human intuition was shaped by forests, rivers, stones, and skies, environments filled with objects and events. Our brains are excellent at imagining things that exist, but imagining the complete absence of existence is something quite different. It is a little like trying to picture a colour that does not exist, or trying to hear a sound that has never been heard. The mind reaches out and finds nothing to grasp. Curiously, the deeper scientists have looked into the universe, the more they have discovered that emptiness is everywhere. Matter, the solid things around us, actually occupies only a tiny fraction of the cosmos. Take something as ordinary as an atom. An atom is often pictured as a tiny solar system, with electrons moving around a central nucleus. But the scale of this structure is astonishing. If an atom were expanded until it was the size of a large sports stadium, the nucleus at its centre would be no larger than a small grain of sand resting on the field. The electrons would be somewhere out near the stadium seats. Almost everything in between would be empty space. The chair you're sitting on, the walls around you, even your own body. At the deepest level, they are built mostly from emptiness. Now imagine zooming outward instead of inward. Between the Earth and the Moon lies a vast stretch of space that is almost entirely empty. Between stars there are distances so enormous that light itself needs years to travel between them. And between galaxies, the great cities of stars scattered across the universe, there are gulfs of darkness spanning millions of light years. The universe, it turns out, is not primarily made of matter. It is primarily made of emptiness. matter appears only here and there, like scattered islands rising from an immense cosmic ocean. For a long time, this idea felt deeply uncomfortable to human thinkers. It seemed strange that nature would allow empty space to exist at all. Many philosophers believed the universe simply would not permit such a thing. One of the most influential of these thinkers lived more than 2,000 years ago in ancient Greece. His name was Aristotle, and his ideas about nature shaped scientific thinking for centuries. Aristotle believed that empty space, a true vacuum, could not exist. In his view, nature itself resisted the creation of emptiness. The universe, he thought, always rushed to fill any gap that appeared. It was a beautiful idea, and one that felt intuitively correct to generations of observers. After all, if you tried to create an empty space in everyday life, by pulling apart objects or drawing air from a container, something always seemed to flow in and replace it. Air rushed into open spaces. Water filled empty cavities. The world appeared to dislike gaps. And so, for nearly 2,000 years, the idea that nature abhors a vacuum remained a guiding belief about how the universe worked. Yet quietly, slowly, small cracks in that idea were beginning to form. Simple experiments with air, pressure, and glass tubes would eventually reveal something surprising, something that Aristotle himself could never have imagined. The universe does allow empty space. In fact, it contains vast oceans of it. And a scientist would later discover that emptiness might not be empty at all, because deep, within the quiet vacuum of space, invisible activity may be unfolding constantly. Tiny flashes of energy appearing and disappearing, like faint ripples on a perfectly calm pond. The deeper we look, the stranger nothing begins to feel. What first appears to be empty silence may actually be one of the most active places in the universe. And that realization begins with something very simple, a curious observation about air pressure, and an experiment involving a glass tube filled with liquid metal. The story of how scientists first learned to create empty space is both surprisingly simple and quietly revolutionary, and it begins not in the distant cosmos, but in a small laboratory on Earth, where a single experiment revealed that the universe might be far more comfortable with emptiness than anyone had ever suspected. When we begin thinking about emptiness, the mind usually starts with something familiar, perhaps an empty room or a quiet stretch of night, sky where only a few stars shine faintly in the distance. But the deeper science has explored the structure of reality, the more it has discovered that emptiness is not a rare condition at all. In fact, it may be the most common state of the universe. To understand why, it helps to return for a moment to something incredibly small, an atom. Atoms are the building blocks of everything around you. The air you breathe, the chair beneath you, the glass on your table, even the cells in your body. For a long time, scientists imagined atoms as tiny solid spheres, like microscopic grains of sand making up the world. But when physicists began probing atoms more carefully in the early 20th century, a very different picture emerged. Inside every atom sits a nucleus, a dense central core made of particles called protons and neutrons. Around that nucleus move lighter particles known as electrons. The surprising part is the scale of the distances involved. If we imagine an atom magnified to the size of a vast sports stadium, the nucleus would be no larger than a small grain of sand resting quietly at the centre of the field. The electrons would move somewhere far out near the stadium walls. Everything in between, the enormous space between the nucleus and the electrons, would be almost completely empty. So the solid objects around us are not truly solid in the way our senses suggest. They are delicate structures of tiny particles separated by enormous gaps of space. Your hands, your chair, your desk, all of them are built mostly from emptiness. This realization can feel almost unsettling at first, as if the solidity of the world has quietly dissolved beneath closer inspection. Yet it also reveals something fascinating about the nature of matter. The stability of objects does not come from packed solidity, but from the delicate balance of forces holding particles in place within those empty spaces. The world, it seems, is built like a vast architectural lattice, more like an intricate scaffolding than a solid block. Now imagine expanding your view outward instead of inward. If atoms are mostly empty space, what about the distances between objects in the cosmos? Consider our own solar system. The Sun, blazing at the centre, contains almost all the mass of the system. The planets move in graceful orbits far away from it, separated by enormous distances. Between the planets lies space that is almost entirely empty. Even the asteroid belt, which might sound crowded when described in books or films, is actually incredibly sparse. Spacecraft can pass through it without difficulty because the individual rocks are separated by vast stretches of open space. Now extend the scale further. The nearest star to our Sun lies more than 4 light-years away. A beam of light, travelling faster than anything else in the universe, takes more than 4 years to cross that distance. Between those stars is a region of space that contains almost nothing at all, and beyond the stars lie galaxies, immense spirals of hundreds of billions of suns scattered across the universe like distant cities of light. Yet even galaxies are separated by unimaginable gulfs of darkness. Millions of light-years may stretch between one galaxy and the next. When astronomers map the large-scale structure of the cosmos, the result resembles a delicate cosmic web. Filaments of galaxies trace faint lines through space, while enormous regions between them contain very little matter. Those vast regions are known as cosmic voids. In some cases, these voids span hundreds of millions of light-years. Within them, there may be only a few scattered galaxies drifting through enormous oceans of emptiness. So when we look at the universe on its larger scales, a remarkable picture emerges. Matter is not the dominant ingredient of reality. Emptiness is. Stars, planets, and galaxies occupy only a tiny fraction of the cosmic volume. Most of existence consists of vast regions of space that contain almost nothing at all. From this perspective, the universe begins to resemble an immense ocean of emptiness in which small islands of matter occasionally appear. This idea leads to a subtle but powerful shift in perspective. Instead of thinking of empty space as the absence of something, scientists increasingly began to view it as the natural background of the universe, the default condition from which structures emerge. Matter, in a sense, may be the rare exception. Emptiness may be the rule. But arriving at this view was not easy. For much of human history, thinkers struggled to accept the idea that empty space could truly exist. Our everyday experiences seem to suggest the opposite. Pour water into a cup, and the water fills the empty space. Open a door and air flows into the room. Remove an object from a container, and something else quickly takes its place. Nature seemed to dislike gaps. This intuition was so powerful that it shaped scientific thinking for centuries. Many philosophers believed the universe itself prevented emptiness from forming. The world, they thought, always rushed to fill any void. It was a comforting idea, one that aligned neatly with everyday observation. But as the centuries passed, curious experimenters began to ask a simple question. What would happen if we tried, very carefully, to remove the air from a container? Would nature truly rush to fill the gap? Or would something unexpected appear instead? The answer began to emerge during the 17th century, when a small group of scientists started performing experiments that would quietly challenge centuries of philosophical belief. Using glass tubes, liquid metals, and careful observation, they discovered something remarkable. Empty space could be created, and when it appeared, nature did not panic or rush to destroy it. Instead, the universe simply allowed it to exist. This realization opened the door to one of the most profound discoveries in the history of science, the understanding that vacuum is not only possible, but widespread throughout the cosmos. Yet even this discovery was only the beginning, because centuries later, physicists would learn something even stranger. The vacuum of space, the vast emptiness filling most of the universe, might not be empty at all. Hidden within it could be subtle activity, invisible energy, and fleeting flashes of particles appearing and disappearing too quickly for the eye to see. But that extraordinary realization began with a much simpler insight. Air has weight, and proving that simple fact would require a beautifully elegant experiment involving a glass tube, a basin of mercury, and a scientist curious enough to question the ancient belief that nature could never tolerate emptiness. Long before laboratories, telescopes, or particle accelerators existed, human beings tried to understand the universe using observation, logic, and careful thought. Among the many thinkers who attempted this, one figure stood above the rest in influence. His name was Aristotle, and his ideas shaped scientific understanding for nearly 2,000 years. Aristotle lived in ancient Greece more than 3 centuries before the birth of the Roman Empire. He studied the natural world with extraordinary curiosity, asking questions about motion, matter, the sky, and the nature of reality itself. In many ways, Aristotle helped build the first systematic picture of how the universe might work. But when it came to the idea of empty space, the possibility of true nothing, Aristotle found the concept deeply troubling. To him, a universe containing emptiness did not make sense. He believed that nature itself resisted the formation of empty space, almost as if the universe preferred to remain full. From this belief emerged a phrase that would echo through centuries of scientific thought: nature abhors a vacuum. At first glance, this idea feels strangely intuitive. Our everyday experiences often seem to support it. Imagine drinking through a straw. When you draw air out of the straw, the liquid rises upward to replace the space you created. It feels as though the universe itself is rushing to fill the gap. Or imagine pulling apart 2 flat surfaces that have been pressed tightly together with a thin film of water between them. As you separate them, resistance appears, almost as if empty space does not want to form between the surfaces. Even simple observations with containers and liquids appear to suggest that nature dislikes emptiness. Remove water from a bottle, and air flows in immediately. Create a gap anywhere, and something quickly fills it. To Aristotle and many thinkers after him, these observations seem like strong evidence. They believed that motion itself required a medium, some substance through which objects could move. In their view, if a true vacuum existed, objects moving through it would encounter no resistance at all. Without resistance, Aristotle reasoned there would be nothing to limit the speed of motion. Objects might accelerate infinitely fast, which seemed impossible and illogical. From this reasoning, he concluded that empty space could not exist. The universe must always remain filled with something. It was a beautifully coherent idea, fitting neatly with the everyday experiences people observed around them. For centuries, Aristotle's explanation of nature shaped scientific thinking across Europe, the Middle East, and parts of Asia. His writings were studied, copied, translated, and taught generation after generation. Because Aristotle was so influential, his conclusions were rarely questioned. Instead, scholars worked within his framework, refining details while accepting the central idea that vacuum could not exist. Yet occasionally, curious observations would appear that didn't quite fit this picture. For example, wells used to draw water from underground sometimes produced Puzzling results. When workers tried to pump water upward through long pipes, they discovered that the water could only rise to a certain height before stopping. No matter how strong the pump was, the water refused to climb any higher. At first, this seemed mysterious. If pumps were pulling water upward, why would there be a limit? Some people suggested that nature simply refused to allow a gap to form inside the pipe. If the water rose too high, a vacuum would appear below it, something nature supposedly avoided. So perhaps, they reasoned, the universe was preventing the pump from creating empty space. For many years, this explanation felt satisfactory, but as the scientific revolution slowly began to unfold during the 16th and 17th centuries, a new spirit of investigation began to take hold. Instead of relying only on philosophical reasoning, scientists started designing careful experiments to test ideas directly. They began asking a simple but powerful question: what actually happens if we deliberately try to create empty space? Would nature truly resist it? Or would something else occur? Answering that question required a scientist willing to challenge centuries of accepted wisdom. In the early 1700s, that scientist appeared in Italy. His name was Evangelista Torricelli, a student of the famous astronomer Galileo. Torricelli was fascinated by the puzzling behavior of water pumps and the mysterious limit on how high water could be lifted. Rather than accepting the traditional explanation that nature feared emptiness, he wondered if something else might be responsible. Perhaps the problem was not the pump at all. Perhaps the air itself, the invisible atmosphere surrounding Earth, was playing a role. Torricelli began thinking about air in a new way. Instead of imagining it as something weightless and passive, he wondered whether air might actually press down on the surface of the Earth with a subtle but measurable force. If that were true, then perhaps the atmosphere itself was holding water up inside the pump. And if the air could hold water up, then maybe it could hold something heavier as well. To test this idea, Torricelli designed an elegant experiment involving a long glass tube and a dense liquid metal known as mercury. What he observed would surprise the scientific world. When the experiment was complete, the mercury inside the tube did something remarkable. It fell partway down, but not all the way. And at the very top of the tube, something extraordinary appeared. A space that contained no air. A space that seemed to be truly empty. For the first time in history, a laboratory experiment had produced what appeared to be a genuine vacuum. If Torricelli's interpretation was correct, then the universe did not fear empty space at all. Instead, the atmosphere was simply pressing down with its weight, holding the column of liquid in place. The ancient idea that nature could never allow a vacuum was beginning to crack, and with that small glass tube filled with liquid metal, the long journey toward understanding the true nature of nothing had quietly begun. In the middle of the 17th century, the question of empty space was no longer just a philosophical puzzle. It had quietly become an experimental mystery. Water pumps across Europe had been revealing something strange for decades. No matter how powerful the pump, water drawn from deep wells would only rise to a certain height inside the pipe. After that point, it simply refused to go any higher. The limit appeared again and again, almost like a hidden rule of nature. Many people believed they already knew the explanation. According to the old idea that nature avoids emptiness, the water was being pulled upward only until the universe could no longer prevent a vacuum from forming below it. In other words, the water stopped rising because nature refused to allow an empty space to appear inside the pipe. For centuries, this explanation seemed reasonable, but Evangelista Torricelli began to suspect that something else was happening. Torricelli had studied under Galileo, one of the pioneers of careful observation and experiment. Like his teacher, he believed that nature should be tested directly, rather than explained only through philosophical reasoning. Torricelli wondered if the answer might lie not in the pump, but in the air around us. Although air feels light and almost invisible, Torricelli considered the possibility that it might have weight. If the atmosphere above us presses downward, then perhaps it is capable of pushing liquids upward into pipes. In this picture, the pump would not be pulling water up at all. Instead, the surrounding air would be pushing it upward. To explore this idea, Torricelli designed a beautifully simple experiment. He took a long glass tube sealed at one end and filled it completely with mercury. Mercury as a liquid metal is much heavier than water, making it especially useful for experiments involving pressure. Once the tube was filled, he carefully covered the open end with his thumb and turned the tube upside down into a basin also containing mercury. Then he slowly removed his thumb from the opening. At first, the mercury inside the tube began to slide downward into the basin. But then something surprising happened. Instead of draining out completely, the mercury stopped partway down the tube. A tall column of the liquid remained suspended inside the glass, while the space above it appeared completely empty. This space contained no visible air, no vapor, and no liquid. It was a void. The mercury had settled at a height of roughly 76 centimeters above the surface of the basin. No matter how many times the experiment was repeated, the result remained nearly the same. Torricelli had discovered something remarkable. The column of mercury was not being held up by a mysterious dislike of emptiness. Instead, it was being supported by the pressure of the atmosphere pressing down on the surface of the mercury in the basin. The air around us, though invisible, behaves like a vast ocean surrounding the Earth. Every moment of every day, the atmosphere presses gently downward on everything beneath it. The ground, the oceans, the trees, and even our bodies. Normally, we do not notice this pressure because it acts equally in all directions. But in Torricelli's experiment, the effect became visible. The weight of the air above the basin pushed on the mercury below, holding the column of liquid up inside the glass tube. The mercury rose until the downward weight of the liquid column balanced the upward push of the atmosphere. Above that column, a space remained where no air could reach. For the first time in history, scientists had created a stable vacuum in the laboratory. The discovery was quietly revolutionary. If the top of the tube truly contained empty space, then Aristotle's famous idea that nature cannot tolerate a vacuum was no longer correct. Nature was perfectly capable of allowing emptiness to exist. The universe did not rush in to destroy the vacuum. It simply allowed it to remain. Torricelli himself recognized the importance of what he had found. In describing the experiment, he suggested that we live at the bottom of an ocean of air. This invisible ocean stretches upward for many kilometers above the Earth's surface, and its weight presses down on everything below. It was a striking new way of imagining our place in the world. Instead of standing beneath an empty sky, we are immersed within a vast atmosphere that surrounds the planet like a transparent sea. And beyond the upper reaches of that sea lies something even more extraordinary: the near-perfect vacuum of outer space. But in Torricelli's time, the implications of the experiment were still unfolding. Other scientists soon began repeating the test, curious to see whether the height of the mercury column might change under different conditions. One of the most famous of these follow-up experiments was carried out by the French mathematician and philosopher Blaise Pascal. Pascal wondered whether the height of the mercury column might vary depending on altitude. If the atmosphere truly behaved like an ocean of air pressing downward, then the pressure should become weaker as one climbed higher above the Earth. To test this idea, Pascal arranged for a mercury barometer, essentially Torricelli's glass tube experiment, to be carried up the side of a mountain. As the device moved higher and higher above sea level, observers carefully measured the height of the mercury column inside the tube. Just as Pascal predicted, the column slowly dropped. At higher altitudes, where less air existed above the observer, the atmosphere pressed downward with slightly less force. The mercury column inside the tube became shorter. With this simple mountain experiment, Pascal confirmed that the air surrounding our planet truly has weight. Together, the experiments of Torricelli and Pascal transformed the way scientists understood the atmosphere and the nature of empty space. They showed that vacuum was not a forbidden condition of nature. It could be created, it could exist. And once scientists learned how to produce vacuum reliably, they discovered something unexpected. The study of empty space would unlock entirely new areas of physics, leading to the discovery of electrons, X-rays, and many of the technologies that shape the modern world. But those discoveries were still far in the future. For now, the most important lesson was simple and profound. Nature does not fear empty space. Instead, emptiness quietly surrounds us everywhere. From the space inside laboratory tubes to the vast dark regions between the stars, and as later generations of physicists would eventually discover, that emptiness may hold more activity than anyone once imagined. Once Torricelli had shown that a column of mercury could stand suspended inside a glass tube, supported only by the invisible pressure of the surrounding air, the world suddenly looked a little different. Something people had rarely thought about before, the air itself, had quietly become a physical presence. It was no longer just the empty background through which birds flew and clouds drifted. The atmosphere now appeared as a real substance with weight, capable of pressing on everything below it. Yet this idea still felt strange to many people. Air seemed too light, too intangible to possess weight in the same way that water or stone does. You could move your hand through it effortlessly. You could not see it, and most of the time you could barely feel it. And yet Torricelli's experiment had shown that the atmosphere could hold up a heavy column of liquid metal inside a glass tube. To understand this better, it helps to imagine the Earth surrounded by a vast invisible ocean. Not an ocean of water, but an ocean of air. Just as fish swim beneath the surface of the sea, we live at the bottom of this enormous atmospheric ocean. Above us stretch many kilometers of air, stacked layer upon layer, gradually thinning as they extend upward towards space. All of that air has mass, and the weight of that mass presses downward. Normally, we do not notice this pressure because our bodies are perfectly adapted to it. The air pushes inward from all directions, while the fluids inside our bodies push outward with equal strength. The forces balance each other quietly and comfortably. But instruments like Torricelli's mercury tube reveal the presence of that pressure very clearly. When the atmosphere presses down on the surface of the mercury in the basin, it supports the tall column of liquid inside the glass tube. The system settles into a delicate balance, where the downward weight of the mercury column matches the upward push of the air outside. In effect, the atmosphere acts like a giant invisible hand supporting the column from below. This simple insight opened the door to a remarkable new tool. Torricelli's apparatus became known as a barometer, an instrument used to measure atmospheric pressure. By observing the height of the mercury column, scientists could determine how strongly the atmosphere was pressing downward at any particular place. And when Pascal carried the instrument up the side of a mountain, something remarkable happened. The mercury column became shorter. This small change revealed a profound truth. The higher you travel above the Earth, the less air remains above you. At the base of the mountain, the observer stands beneath the full weight of the atmosphere. Higher up the slope, part of that air is now below rather than above the instrument, so the pressure becomes slightly weaker. By the time you reach the summit, the atmosphere pressing down from above is noticeably thinner. The barometer had become a window into the structure of the sky. This realization gradually transformed the way scientists imagine the boundary between Earth and space. Instead of a sharp edge separating the atmosphere from the heavens, they began to understand that the air simply becomes thinner and thinner as altitude increases. Eventually, at great heights, the air becomes so sparse that it can hardly be detected at all. Beyond that point lies the near-perfect vacuum of outer space. The discovery that air has weight also helped solve several everyday mysteries. For example, it explained why water pumps in wells could only raise water to a certain height. The pump itself was not pulling the water upward indefinitely. Instead, it was removing air from the pipe, allowing the surrounding atmosphere to push water up into the empty space. But the atmosphere could only push with a limited strength. Once the column of water became tall enough, its weight balanced the pressure of the air below. At that point, the water simply stopped rising. The limit that had puzzled observers for years was not caused by nature's fear of vacuum at all. It was caused by the finite weight of the air pressing down upon the Earth. This was a quiet but profound shift in understanding. Where ancient philosophers had seen a mysterious force preventing emptiness, scientists now saw a measurable physical phenomenon: atmospheric pressure. And once this new perspective took hold, curiosity about empty space began to grow rapidly. Scientists started building improved vacuum pumps, devices capable of removing more and more air from sealed containers. As these technologies improved, experimenters were able to create increasingly empty spaces inside glass chambers. What they discovered inside those chambers would lead to some of the most important scientific breakthroughs of the 19th century. When the air inside a glass tube was removed almost completely, strange things began to happen. Electrical currents passing through the near-empty tubes produced glowing streams of light. These faint luminous beams fascinated physicists. At first they appeared mysterious, almost ghost-like, but eventually they would reveal something astonishing about the structure of matter itself. Inside those vacuum tubes, scientists were observing streams of tiny charged particles. Those particles would later be named electrons. In other experiments, vacuum tubes produced invisible radiation capable of passing through solid objects and revealing images of bones hidden beneath skin. These mysterious rays would later become known as X-rays. Step by step, the study of empty space was opening doors to entirely new areas of science. What had once been dismissed as impossible, the creation of vacuum, was now becoming one of the most powerful tools in experimental physics. By removing air from an environment, scientists could observe phenomena that would otherwise remain hidden. Tiny particles could travel freely without colliding with gas molecules. Electrical effects could unfold in ways that were impossible in ordinary air. Vacuum chambers became laboratories for exploring the invisible world of atoms and subatomic particles. And with each discovery, the idea of emptiness became stranger. The vacuum that philosophers once feared was not simply an absence of matter. It was a place where unexpected phenomena could appear: light, radiation, particles, and forces that seemed to emerge from the emptiness itself. Slowly, a new suspicion began to form. Perhaps empty space was not truly empty after all. Perhaps the vacuum was hiding something. For centuries, scientists had believed that light must travel through a medium, just as sound travels through air or waves travel through water. If that were true, then even the vacuum of space might contain an invisible substance carrying light across the universe. And so, during the 19th century, a new idea took shape. A mysterious medium was proposed, one that would quietly fill the entire cosmos. Scientists called it the ether. By the time scientists had learned to create vacuum inside glass tubes, the ancient belief that empty space could never exist had finally faded. Experiments had shown clearly that air could be removed from a container. A vacuum could appear, and when it did, nature did not rush to destroy it. Instead, the empty space simply remained. Yet, as often happens in science, solving one mystery quietly revealed another. Once physicists began studying vacuum carefully, they noticed something strange about the way different phenomena behaved inside it. Sound, for example, behaved exactly as expected. Imagine placing a small ringing bell inside a sealed glass chamber. As long as the chamber contains air, the bell rings normally. Vibrations travel through the air to your ears, and you hear the familiar chime. Now imagine slowly pumping the air out of the chamber. As the air disappears, the sound of the bell begins to fade. The bell is still moving, still vibrating, but less and less sound reaches the outside world. Eventually, the chamber becomes nearly empty. Inside, the bell continues to shake back and forth, but outside the glass there is silence. The reason is simple. Sound needs a medium, a material through which vibrations can travel. In everyday life, that medium is usually air. When the air is gone, the vibrations have nothing to carry them. Sound cannot cross empty space. So far, everything made perfect sense. But light behaved differently. If you shine a flashlight through a vacuum chamber, the beam of light continues to travel without difficulty. Even when almost all the air has been removed, the light still crosses the empty space easily. This observation raised a puzzling question. If sound waves require air to travel, then what allows light to move through the vacuum of space? To 19th century scientists, the answer seemed obvious. Light must also travel through some kind of medium. After all, experiments had already shown that light behaves like a wave, and every wave known at the time needed something to move through. Ocean waves move through water, sound waves move through air, ripples move across the surface of a pond. So if light is a wave, it must also ripple through some kind of substance. But that substance could not be ordinary matter, because light travels through the emptiness between stars and planets. The medium would have to be extremely subtle, something invisible, weightless, and capable of filling every corner of the universe. Scientists gave this mysterious substance a name. They called it the luminiferous ether. The ether was imagined as an invisible ocean permeating all of space. Planets, stars, and galaxies would drift through it much like fish swimming through water. Light waves in this picture would be tiny ripples moving through this cosmic sea. The idea solves several puzzles at once. If ether filled the vacuum of space, then light could travel through it just as sound travels through air. The universe would never truly be empty. Even the darkest regions between stars would still contain this invisible medium. For many scientists, the ether seemed like a perfectly reasonable solution. Yet the concept carried an unusual set of properties. The ether would have to be incredibly thin so that planets could move through it without resistance. If it behaved like a normal fluid, the motion of the Earth through the ether would slow our planet down over time. But at the same time, the ether would need to be strong enough to support the incredibly fast vibrations of light. It was as if the universe were filled with a substance that was both almost nothing and yet somehow capable of carrying waves of energy across unimaginable distances. Physicists spent many years trying to understand the nature of this strange medium. Some imagined it as an elastic structure stretching throughout space. Others pictured it as a subtle fluid that could not be directly detected. But if the Earth moved through this invisible ocean of ether, then perhaps that motion could be measured. Imagine walking through still air. Even if you move slowly, you feel a gentle breeze against your face. The faster you walk, the stronger the wind appears. In a similar way, if the Earth travels through the ether as it orbits the Sun, then there should be a kind of ether wind blowing past the planet. And if such a wind existed, it should slightly affect the speed at which light travels in different directions. This idea suggested a clever experiment. If scientists could measure the speed of light very precisely along different directions, they might detect the subtle influence of the Earth moving through the ether. In other words, the Earth should feel a faint cosmic breeze as it drifts through the invisible medium of space. Detecting that breeze would confirm the existence of ether once and for all. By the late 19th century, physicists had developed instruments sensitive enough to attempt such a measurement. One of the most ambitious experiments designed to search for this invisible medium would soon be carried out by two American scientists. Their names were Albert Michelson and Edward Morley. Using an exquisitely precise instrument built to measure the motion of light itself, they set out to detect the faint whisper of the ether wind. What they discovered would become one of the most surprising results in the history of science. Because when the experiment was completed, something astonishing appeared. The ether wind was nowhere to be found. Light seemed to travel through empty space exactly the same way in every direction, as if the mysterious medium filling the universe simply did not exist. The experiment that followed would quietly shake the foundations of physics and open the door to an entirely new understanding of space, light, and the nature of the vacuum itself. Time equals, quote, 2 seconds, quote / greater than. By the 19th century, scientists had grown increasingly comfortable with the idea that empty space could exist. Vacuum chambers had been created in laboratories. Air could be pumped out of glass tubes. Experiments had shown clearly that nature did not panic when empty space appeared. And yet a puzzle remained. Light still travelled effortlessly across the vacuum. When you shine a beam of light through empty space, nothing seems to slow it down. It crosses the darkness between stars, between planets, and even between galaxies. To modern readers, that fact may seem ordinary, but to scientists of the 19th century, it raised an uncomfortable question. If light behaves like a wave, what exactly is waving? At the time, waves were understood only through familiar examples. Ocean waves travel through water. Sound waves travel through air. Ripples move across the surface of a pond. In every case, a wave was a pattern of motion passing through some kind of material. Without a medium, the wave simply could not exist. So when experiments revealed that light behaved like a wave, bending, reflecting, and interfering with itself in delicate patterns, scientists concluded that light must also travel through a medium. But that medium could not be ordinary matter. Light clearly passed through the vacuum of space where no air existed. It crossed enormous distances between stars where almost nothing could be found. Therefore, the medium carrying light must be something far more subtle, something invisible, something present everywhere. Gradually, physicists began imagining a mysterious substance that filled the entire universe. They called it the luminiferous ether. The word luminiferous simply meant light-carrying. The ether in this picture was the invisible ocean through which light waves travelled. The idea was strangely elegant. Just as fish move through water, planets and stars would drift through this cosmic sea. The vacuum of space would not truly be empty after all. Instead, it would be filled with an incredibly delicate substance that our senses could not detect. Light, then, would simply be tiny ripples moving through this invisible ocean. At first, the concept seemed to solve several problems at once. It explained how light could behave like a wave while still travelling across the emptiness of space. It preserved the familiar idea that waves always require a medium, and it allowed scientists to maintain a comfortable continuity between the physics of everyday life and the physics of the cosmos. Yet the ether carried a strange list of requirements. For one thing, it had to be extraordinarily thin. Planets move through space at enormous speeds. The Earth alone travels around the Sun at roughly 30 kilometers each second. If the ether behaved like an ordinary fluid, the motion of planets through it would create resistance. a kind of cosmic friction that would gradually slow their orbits, but no such slowing was observed. The planets moved smoothly, year after year, century after century, so the ether had to be thin enough that objects could move through it without resistance. At the same time, the ether also had to be remarkably rigid. Like waves vibrate extremely quickly. To support those vibrations, the medium carrying them would need to transmit motion with extraordinary speed. In other words, the ether had to behave like a substance that was both extremely delicate and extremely strong at the same time. To modern ears, this combination may sound suspicious, but to physicists of the 19th century, it seemed entirely reasonable. After all, the universe had often revealed hidden structures that were difficult to imagine at first. Electricity and magnetism had already been discovered as invisible forces filling space. Fields of energy could extend through empty regions and influence objects at a distance. Why should there not also be an invisible substance filling the cosmos? And so the ether became an accepted part of scientific thinking. Textbooks described it. Theories relied upon it. Scientists spoke of it as confidently as they spoke of gravity or light. Yet the ether had one curious feature. No one had ever observed it directly. No instrument had detected its presence. No experiment had measured its properties. The ether remained an invisible stage upon which light waves were thought to move. Still, physicists believed that its existence must eventually reveal itself through careful measurement. One particular idea seemed especially promising. If the Earth moves through the ether as it orbits the Sun, then the planet must be drifting through this invisible ocean. And if that is true, then there should be something like a faint cosmic breeze, a gentle flow of ether past the Earth. Imagine riding a bicycle on a calm day. Even if the air around you is perfectly still, you feel wind against your face as you move forward. The faster you ride, the stronger the breeze becomes. In the same way, if Earth moves through the ether, the motion of our planet should create a kind of ether wind. This invisible wind should slightly affect the speed of light depending on which direction the light travels. A beam moving in the same direction as the ether wind might move a little differently than one travelling across it. The difference would be extremely small, but by the late 19th century, physicists had developed instruments capable of detecting astonishingly tiny changes in distance and time. If ether truly filled the universe, then surely its effects could be measured. All that remained was to design an experiment delicate enough to reveal it. Two American physicists decided to try. Their names were Albert Michelson and Edward Morley. Using an instrument built with extraordinary precision, they attempted to detect the faint whisper of the ether wind as the Earth moved through space. The experiment was elegant, careful, and incredibly sensitive. If the ether existed, their instrument should reveal it. But when the measurements were finally completed, the results were not what anyone expected. The ether wind was nowhere to be found. Light appeared to travel at exactly the same speed in every direction, as if the invisible ocean filling the universe simply did not exist at all. What seemed like a minor experimental puzzle would soon become one of the most important turning points in the history of physics, because explaining that strange result would eventually lead scientists to a new understanding of space itself, and to one of the most revolutionary ideas ever proposed about the nature of the universe. By the late 19th century, the idea of ether had become deeply woven into the fabric of physics. Most scientists believe that space must contain this invisible medium, a delicate substance filling the universe and carrying waves of light across cosmic distances. The concept seemed almost unavoidable. Light behaved like a wave. Waves needed something to travel through. Therefore, space must be filled with something. But science has a quiet rule that guides every discovery. Ideas must eventually face experiment. No matter how elegant a theory appears, it must be tested against the behaviour of the real world. If ether truly filled the universe, then the Earth should be moving through it as it travelled around the Sun. And if the Earth was moving through this invisible medium, then a subtle effect should appear, something physicists began calling the ether wind. The idea was simple. Imagine standing outside on a calm day. The air around you may be perfectly still, but if you begin to run forward, you feel a breeze against your face. The faster you move, the stronger the wind seems to blow. In this situation, the air itself has not changed. The wind appears because you're moving through it. Physicists imagined that something similar might happen as the Earth moved through the ether. Our planet travels through space at enormous speed. As it circles the Sun, it moves tens of thousands of kilometers each hour. If the ether filled the universe, the Earth would constantly be drifting through it. That motion should create a faint ether wind flowing past the planet. And if that wind existed, it should influence the motion of light in a very subtle way. A beam of light travelling in the same direction as the ether wind might move slightly differently than one travelling across it. The difference would be extremely small, far too tiny to notice in everyday experience. But by the 1880s, physicists had developed instruments capable of measuring incredibly small changes in the path of light. One of the scientists who specialised in such measurements was Albert Michelson. Michelson was known for his extraordinary skill in building precise optical instruments. His work focused on measuring the speed of light with unprecedented accuracy. To test the existence of ether wind, Michelson collaborated with another physicist, Edward Morley. Together they designed an experiment of remarkable elegance. At the heart of their device was an instrument called an interferometer. Although the name may sound complex, the basic idea is beautifully simple. A beam of light is first split into two identical paths. Each beam travels along a different direction before being reflected back to meet again at the starting point. When the two beams reunite, they create a pattern of light and dark stripes known as an interference pattern. This pattern is extremely sensitive. Even the tiniest difference in the distance travelled by the beams can shift the stripes slightly. Michelson realised that this sensitivity could reveal the presence of the ether wind. If the Earth were moving through ether, then one beam of light, travelling along the direction of motion, should take a slightly different amount of time to complete its journey, compared with the beam travelling across the motion. The difference would be incredibly small, but the interference pattern should shift in a measurable way. To perform the experiment, Michelson and Morley built their interferometer on a massive stone platform designed to reduce vibrations. The entire apparatus floated on a pool of mercury, allowing it to rotate smoothly. By slowly turning the instrument, they could measure the speed of light along different directions. If the ether wind existed, rotating the apparatus should cause the interference pattern to shift as the direction of motion changed. It was a brilliant design. The experiment was performed in 1887 in Cleveland, Ohio. With great care, Michelson and Morley conducted their measurements again and again. They rotated the instrument. They observed the interference pattern. They recorded every subtle movement of the light stripes. Then they repeated the measurements and repeated them again. But something strange happened. The expected shift in the interference pattern never appeared. No matter how the instrument was rotated, the pattern remained essentially unchanged. Light seemed to travel at exactly the same speed in every direction. The ether wind could not be detected. At first, Michelson himself was reluctant to draw strong conclusions. Perhaps the ether behaved differently than expected. Perhaps the Earth dragged the ether along with it somehow. Physicists proposed various adjustments to the theory in an attempt to preserve the idea of ether. But as more experiments were performed over the following years, the same result continued to appear. The ether wind remained invisible. Eventually, the simplest explanation began to emerge. Perhaps the ether did not exist at all. This possibility was deeply unsettling to many scientists. The ether had been imagined as the foundation upon which waves of light travelled. Without it, the behaviour of light seemed mysterious once again. If light did not require a medium, then how could it move through empty space? The Michelson-Morley experiment did not immediately answer that question. Instead, it left physicists with a puzzle that seemed almost impossible to resolve. How could light behave like a wave while travelling through a vacuum that contained nothing? The answer would come from an unexpected direction. A young physicist working in Switzerland began thinking carefully about the nature of space, time, and the speed of light itself. His name was Albert Einstein, and the idea he proposed would completely transform our understanding of light, motion, and the structure of the universe. The strange silence of the ether wind left physicists facing a puzzle. The Michelson-Morley experiment had been designed with extraordinary care. Its instruments were sensitive enough to detect incredibly tiny differences in the motion of light. If the Earth were drifting through an invisible ocean of ether, even the faintest whisper of that motion should have appeared in the experiment. But the result was unmistakable. Light behaved the same in every direction. It did not seem to care how the Earth moved through space. The speed of light appeared constant no matter which way the instrument was turned. At first, many scientists tried to rescue the idea of ether by adjusting the theory. Perhaps the ether moved along with the Earth somehow. Perhaps objects changed shape slightly as they moved through the medium. Several clever mathematical ideas were proposed to explain why the ether wind remained hidden. Yet these solutions felt increasingly complicated. Then, in the early years of the 20th century, a young physicist working in Switzerland approached the problem from an entirely different direction. Albert Einstein was not trying to detect ether or preserve it. Instead, he asked a simpler question. What if the speed of light is always the same no matter how the observer's moving? At first, this idea may sound ordinary. After all, when we observe light in everyday life, it seems to behave consistently. But in the physics of motion, the idea was radical. To understand why, imagine a familiar situation. Suppose you are sitting in a train moving steadily along a track. If you throw a ball forward inside the train, the ball moves faster relative to the ground than it does relative to you. Your motion adds to the motion of the ball. This simple rule works for many everyday objects. If you run forward while throwing a ball, the ball's speed increases relative to someone standing still. For centuries, physicists assumed that light would behave the same way. If the Earth moves through space and emits a beam of light, the motion of the Earth should add to the speed of the light in one direction and subtract from it in another. That expectation is exactly what the Michelson-Morley experiment was designed to detect. But the experiment showed something different. Light always travelled at the same speed. It didn't matter whether the observer moved toward the light, away from it, or across its path. The speed remained unchanged. Einstein took this strange observation seriously. Instead of trying to explain why the ether wind was hidden, he proposed a new principle. The speed of light in empty space is always the same for every observer. No matter how fast you move, no matter where you are in the universe, a beam of light always travels at the same constant speed. If this idea is true, then something surprising must happen. The universe must adjust the measurements of space and time themselves in order to keep the speed of light unchanged. This insight formed the foundation of Einstein's theory of relativity. In this new view of physics, space and time were no longer fixed and absolute. Instead, they became flexible quantities that could stretch or compress depending on motion. Imagine two observers moving relative to each other, perhaps two spacecraft, passing silently in the darkness of space. Each observer measures distances and durations slightly differently. Their clocks tick at slightly different rates, and their rulers measure slightly different lengths. These changes are usually far too small to notice in everyday life, but at very high speeds, close to the speed of light, the effects become significant. Time itself can slow down, distances can shrink. The universe quietly reshapes measurements so that the speed of light always remains constant. One of the most beautiful consequences of Einstein's work is the realization that light does not need a medium to travel through. Instead, light is a self-sustaining ripple of electric and magnetic fields. You can imagine it as a delicate dance between two invisible partners. As the electric field changes, it generates a magnetic field. As the magnetic field changes, it regenerates the electric field again. This continuous exchange allows the wave to move forward through space, without needing any material substance to support it. Light, in other words, carries its own motion with it. The universe does not require an ether to transport it. With this realization, the long search for the invisible medium came quietly to an end. The vacuum of space, once imagined as an ocean of ether, now appeared to be truly empty. Space itself was enough. For a moment it seemed as though the story of emptiness had finally reached a simple conclusion. The universe contained vast regions of vacuum, and those regions were simply empty. Yet science has a curious habit of turning simple answers into deeper mysteries. Just as physicists began to accept the idea of a clean and quiet vacuum, a new branch of science began to emerge, a field that explored the strange behavior of matter and energy at extremely small scales. This field was called quantum mechanics, and it would reveal something astonishing. According to quantum physics, empty space may not remain empty at all. Even the quiet vacuum can flicker with subtle activity. Tiny bursts of energy appearing and disappearing in ways that challenge our intuition about nothingness. In the coming chapters of this story, the calm emptiness of the vacuum will begin to feel less like a silent void and more like a restless sea. But before we explore that strange new world, we must first understand a simple idea that sits at the heart of quantum physics. It is the idea that, at the smallest scales of nature, there are limits to how precisely we can know the world, and those limits change the meaning of emptiness itself. By the early 20th century, physics seemed to have reached a comfortable understanding of the vacuum. The ether had been abandoned. Einstein had shown that light did not require a hidden medium to travel through space. The universe appeared to consist of matter scattered through vast regions of emptiness, with light moving freely through the quiet vacuum between stars. For a brief moment, the story seemed simple. Empty space was simply empty. But while Einstein was reshaping our understanding of space and time, another revolution was unfolding in laboratories across Europe. Physicists studying atoms began noticing strange behavior that could not be explained using the familiar rules of classical physics. Atoms did not behave like tiny solar systems. Electrons did not move around the nucleus in smooth, predictable orbits. Instead, their behavior appeared fuzzy, unpredictable, almost dreamlike. To describe this strange new world, scientists began developing a new framework for understanding nature. This framework became known as quantum mechanics. At the heart of quantum mechanics lies a deeply surprising idea. There are limits to how precisely certain properties of nature can be known at the same time. One of the physicists who helped uncover this principle was the German scientist Werner Heisenberg. Heisenberg realized that when we try to measure the position of a very small particle, such as an electron, the act of measurement itself inevitably disturbs the particle. At everyday scales, this effect is so tiny that it goes unnoticed. But at the scale of atoms and subatomic particles, the disturbance becomes significant. Heisenberg's insight eventually led to a principle that would become one of the central ideas of quantum physics. Certain pairs of properties, such as position and motion, cannot both be known with perfect precision at the same time. If you measure the position of a particle very accurately, its motion becomes more uncertain. If you measure its motion very precisely, its position becomes more uncertain. This is not simply a limitation of our measuring instruments. It is a fundamental feature of how nature behaves at the smallest scales. To picture this idea more comfortably, imagine trying to understand the motion of a hummingbird. If you take a perfectly sharp photograph of the bird in flight, the image reveals its position clearly. You see exactly where the wings are at that instant. But the photograph tells you almost nothing about how the wings are moving. Now imagine filming the hummingbird with a video camera. The motion of the wings becomes clear as they beat rapidly through the air. But any single frame of the video is slightly blurred. The exact position of the wings becomes harder to pin down. In a sense, position and motion compete for clarity. Quantum physics suggests that something similar happens with particles like electrons. Nature itself places a limit on how sharply both properties can be known at once, and this limit carries a remarkable implication for the vacuum of space. Another pair of properties governed by quantum uncertainty involves energy and time. In simple terms, the rules suggest that if we look at extremely tiny intervals of time, the amount of energy present in a region of space cannot be perfectly fixed. For very short moments, small fluctuations in energy are allowed. You can imagine the vacuum not as a perfectly still surface, but more like the calm surface of a lake that occasionally produces faint ripples. For brief instants, tiny bursts of energy may appear and then disappear again. These fluctuations happen so quickly that they usually leave no lasting trace. Yet according to quantum theory, they are unavoidable. Even if we remove every particle from a region of space, even if we create the most perfect vacuum possible, the energy within that space cannot remain completely zero at every instant. Instead, it gently flickers. The vacuum becomes restless. Physicists sometimes describe this idea using a simple metaphor. They say that energy can briefly be borrowed from empty space, as long as it is returned almost immediately. The borrowing cannot last long. The universe balances its books quickly. But for extremely short intervals of time, small amounts of energy may appear within the vacuum, and when energy appears in space, something remarkable can happen. According to Einstein's insight that energy and matter are closely connected, energy can transform into particles. Under the right conditions, a tiny burst of energy in the vacuum may briefly produce a pair of particles, one made of matter, the other made of antimatter. The pair appears suddenly, exists for an incredibly short moment, and then vanishes again as the particles annihilate each other. These fleeting particles are known as virtual particles. They cannot normally be observed directly because they exist for such incredibly short periods of time, but their presence can influence the behavior of the universe in subtle ways. In this strange new picture, the vacuum of space is no longer a perfectly quiet void. Instead, it resembles a delicate sea of microscopic activity. Particles flicker into existence and disappear again. Energy ripples through space in tiny fluctuations. What once appeared to be nothing now begins to look like a hidden stage of restless motion. For centuries, philosophers had imagined emptiness as the complete absence of everything. But quantum physics suggests something very different. Even the most perfect vacuum may contain a quiet background of activity, an invisible dance unfolding at scales far smaller than atoms. This idea would soon lead physicists to an extraordinary conclusion. If empty space can briefly produce particles, then perhaps the vacuum itself contains the ingredients necessary to create matter. And if that is true, then the emptiness of space might not merely surround the universe, it might help create it. As quantum physics began reshaping the way scientists understood the microscopic world, the idea of empty space started to feel less stable than it once had. For centuries, emptiness had been imagined as a quiet absence, a place where nothing happens. But the principle of quantum uncertainty suggested something very different. If nature allows small fluctuations of energy to appear for very brief intervals of time, then the vacuum of space cannot remain perfectly still. Instead, it must possess a subtle, almost restless quality. Even when every atom has been removed from a region of space, even when the vacuum seems perfectly empty, tiny bursts of energy may still flicker in and out of existence. These fluctuations occur at scales so small and so brief that they escape direct observation. They are like the faintest ripples on the surface of a lake that appears calm from a distance. Yet the mathematics of quantum theory suggest that these ripples cannot be avoided. The vacuum itself becomes a place of quiet activity. To understand how this works, it helps to imagine the relationship between energy and time as a kind of balance. If a small amount of energy appears for an extremely short moment, nature does not object. The universe allows the fluctuation as long as it disappears quickly enough. The shorter the interval of time, the larger the temporary fluctuation of energy may be. But the borrowed energy cannot remain indefinitely. Within a very brief instant, the balance must be restored. This idea leads to one of the most fascinating consequences of quantum physics. If enough energy appears within a tiny region of space, even for a moment, that energy can transform into particles. Einstein's work had shown that energy and matter are deeply connected. Under the right conditions, energy can be converted into particles of matter. In the quantum vacuum, these conditions occasionally arise for extremely short intervals of time. When they do, pairs of particles may briefly appear. Typically, the pair consists of a particle and its counterpart made of antimatter. Antimatter is similar to ordinary matter, but carries opposite properties in certain ways. For example, an electron, one of the fundamental particles of matter, carries a negative electric charge. Its antimatter partner, called a positron, carries the same amount of charge but with the opposite sign. When matter and antimatter meet, they destroy each other in a burst of energy. This process is known as annihilation. Inside the quantum vacuum, something like this may happen constantly on extremely small scales. A particle and its antimatter partner appear together from a tiny fluctuation of energy. They exist for an incredibly short moment, and then they collide and vanish again, returning their energy back into the vacuum. These fleeting pairs are known as virtual particles. The word virtual does not mean imaginary. Rather, it reflects the fact that these particles cannot be directly observed in the usual way. They appear and disappear too quickly to leave a stable trace, yet their effects can influence the behavior of the universe. Physicists often describe the vacuum as a place where these particle pairs are continuously appearing and disappearing. The process is sometimes compared to the gentle fizzing of sparkling water. If you look closely at a glass of soda, tiny bubbles form throughout the liquid. They appear suddenly, rise for a moment, and then vanish. From a distance, the liquid may seem calm, but up close it contains constant activity. In a similar way, the vacuum of space may appear silent and empty when viewed on large scales, but at extremely small scales it is filled with microscopic bursts of energy and particles. The emptiness is alive with motion. Another way to picture the quantum vacuum is to imagine a vast stage before a performance begins. The curtains are closed. The audience sits quietly. From a distance, the stage appears empty. Yet behind the curtain, preparations are already underway. Lights flicker faintly. Actors move quietly in the shadows. The performance has not yet begun, but the stage is far from inactive. the vacuum may behave in a similar way. What appears to be nothing may actually be a subtle background of invisible activity. These ideas remained largely theoretical when they were first proposed. Physicists could not easily observe the tiny fluctuations of the vacuum directly. But as experiments became more precise, small hints began to appear. Electrons inside atoms behave slightly differently than classical physics predicted. Their motion seemed to be influenced by something invisible surrounding them. Subtle shifts in energy levels hinted that the vacuum itself might be interacting with matter. Slowly, evidence began to accumulate. The vacuum was not simply an absence, it was a dynamic environment, a background field of energy where particles could briefly emerge and vanish again. The implications of this realization were extraordinary. If empty space can momentarily produce particles, then the vacuum must contain a form of energy even when it appears empty. And if the vacuum contains energy, then it may play a role in shaping the structure of the universe itself. The story of nothing was becoming stranger than anyone had imagined. Instead of a silent void, the vacuum was beginning to resemble a vast invisible ocean whose surface is constantly trembling with tiny waves. And as scientists continued exploring this strange new picture of reality, they discovered something even more surprising. The vacuum does not merely allow particles to appear briefly, it can subtly influence the behavior of matter in ways that can actually be measured. In other words, the quiet activity of nothing can leave fingerprints on the physical world. Those fingerprints would soon appear in one of the most delicate experiments ever performed in atomic physics. For a long time, the idea of a restless quantum vacuum existed mostly on paper. Physicists had equations suggesting that empty space could flicker with tiny fluctuations of energy, allowing virtual particles to appear and vanish in fleeting pairs. But science always seeks something more than mathematical beauty. It asks a simple question: can the idea be tested? If the vacuum truly contains subtle activity, then that activity should leave some trace on the behavior of the physical world. Even if we cannot observe the virtual particles directly, their presence might slightly influence the motion of real particles nearby. This possibility fascinated physicists. They began looking for situations where matter might be sensitive enough to reveal the hidden motion of the vacuum. One of the most promising places to search was inside the atom. Atoms are delicate systems. Electrons orbit around a nucleus in patterns that depend on extremely precise balances of energy. If anything disturbs those balances, even slightly, the change can sometimes be detected through careful measurement. In the 1940s, two physicists named Willis Lamb and Robert Rutherford performed an experiment that would reveal something remarkable. Their goal was to study the energy levels of the hydrogen atom. Hydrogen is the simplest atom in the universe. It contains a single proton in its nucleus and a single electron moving around it. Because of this simplicity, hydrogen became a favourite testing ground for theories of atomic physics. According to the best calculations available at the time, certain energy levels inside the hydrogen atom should have been identical. In other words, two different arrangements of the electron were expected to possess exactly the same amount of energy. If that prediction were correct, the two states should behave in precisely the same way. But when Lamb and Rutherford measured the hydrogen atom with extraordinary precision, they found something unexpected. The two energy levels were not exactly the same. One of them was shifted very slightly. The difference was tiny, far too small to notice in everyday experience, but the instruments used in the experiment were sensitive enough to detect it clearly. At first, the result puzzled physicists. Where could this small shift be coming from? There was nothing inside the atom that should produce the effect. The hydrogen atom seemed too simple to hide any complicated internal structure. Gradually a new explanation began to emerge. The shift could be caused by the subtle activity of the quantum vacuum surrounding the electron. Even though the space inside the atom appears empty, the vacuum is constantly flickering with virtual particles. These particles briefly appear, interact with the electron, and then vanish again. Each interaction is incredibly small, but taken together they slightly alter the energy of the electron's motion. It is as if the electron is moving through a faint mist of invisible activity. The result of this interaction is what physicists now call the Lamb shift. This tiny difference in energy levels became one of the first clear pieces of experimental evidence that the quantum vacuum is not truly empty. The vacuum was influencing the atom. Nothing was leaving fingerprints. Another way to imagine this effect is to picture a small boat floating on a calm lake. From a distance, the surface of the water may appear perfectly smooth, but if you look closely, you notice tiny ripples moving across the surface. The boat rises and falls gently with each ripple. If the lake were truly still, the boat would remain perfectly steady. But the faint motion of the water causes small changes in its position. In a similar way, the electron inside an atom moves through a vacuum that contains subtle fluctuations. Those fluctuations shift the electron's energy slightly, just as ripples shift the position of the boat. The Lamb shift provided strong evidence that the vacuum is an active environment rather than a silent void. And once physicists accepted this idea, they began noticing other places where the fingerprints of the vacuum might appear. One example involves two metal plates placed extremely close together in a vacuum. When the plates are separated by only a tiny distance, something curious happens. They experience a very small force pulling them toward each other. This effect is known as the Casimir effect. The force arises because the quantum vacuum behaves slightly differently in the narrow gap between the plates compared with the space outside them. The fluctuations of energy inside the gap become restricted, while the fluctuations outside remain more abundant. The imbalance creates a gentle pressure that pushes the plates together. Although the force is extremely small, modern instruments can measure it. Once again, the vacuum reveals its presence. The emptiness of space is quietly influencing the physical world. Experiments like the Lamb shift and the Casimir effect transformed the way scientists thought about nothingness. The vacuum was no longer an absence of everything. Instead, it became a dynamic background, a field of energy that constantly fluctuates and interacts with matter. In this picture, particles do not simply move through empty space. They move through an environment filled with invisible activity. And this realization opened the door to an even deeper idea. If the vacuum contains energy, then it might possess the ability to shape the universe on the largest scales imaginable. Tiny fluctuations in the vacuum could influence the birth of cosmic structure. Galaxies, stars, and clusters of matter might ultimately trace their origins back to the restless activity of what once seemed to be nothing at all. The story of the vacuum was expanding from the tiny interior of atoms to the enormous architecture of the cosmos. By the early decades of the 20th century, physics had already undergone two profound transformations. Einstein had reshaped the way scientists thought about space and time. Quantum mechanics had revealed that the microscopic world behaved in ways that often defied common sense. Yet the story of the vacuum was still unfolding. The idea that empty space could briefly produce particles was beginning to take shape, but the deeper structure behind that idea had not yet fully emerged. That next step came from an unlikely place. It arrived not through experiment, but through mathematics. In the late 1920s, a British physicist named Paul Dirac was searching for a way to combine two of the most powerful theories of his time. One was quantum mechanics, which described the strange behavior of particles at very small scales. The other was Einstein's theory of relativity, which described how motion and energy behave when objects move extremely fast. Both theories worked beautifully within their own domains. But merging them into a single description of nature proved surprisingly difficult. Dirac believed that such a union should exist. He began exploring the mathematics that might describe an electron, one of the fundamental particles of matter, while fully respecting the principles of both quantum mechanics and relativity. After long effort, he arrived at an equation that seemed to capture exactly what he was seeking. The equation successfully described the motion of electrons at high speeds. It accounted for their quantum behavior and aligned with the requirements of relativity. At first glance, the result appeared to be a triumph. But when Dirac examined the equation more closely, he noticed something strange. The mathematics allowed for two kinds of solutions. One set of solutions described electrons with positive energy, exactly as expected. But another set described particles with the same mass as an electron but with opposite properties. These additional solutions were deeply puzzling. At first, many physicists wondered whether they might simply be mathematical artifacts, strange outcomes produced by the equations but not representing anything real in nature. Dirac himself struggled with the interpretation, yet the equations refused to let the extra solutions disappear. They remained stubbornly present in the mathematics. Gradually, Dirac began to suspect that the equation was revealing something unexpected about the universe. Perhaps the extra solutions represented real particles that mirrored the properties of ordinary matter, but with opposite characteristics. If the electron carries a negative electric charge, then its mirror particle would carry a positive charge of the same magnitude. It would have the same mass. It would obey the same physical laws, but its electric charge would be reversed. Dirac had discovered the concept of antimatter. The particle he predicted became known as the positron, the antimatter counterpart of the electron. At the time, the idea seemed almost fantastical. For centuries, matter had been regarded as the fundamental substance of the universe. Now physics was suggesting that every particle of matter might possess a mirror partner, and these partners could annihilate each other when they met. When a particle of matter encounters its antimatter counterpart, the two can vanish together, releasing their mass as pure energy. It is a process both elegant and dramatic. Two objects meet, both disappear, and a flash of energy remains. Just a few years after Dirac proposed the existence of antimatter, experimental evidence arrived. In 1932, the American physicist Carl Anderson was studying cosmic rays, energetic particles arriving from space, when he noticed tracks in his detector that behaved exactly as Dirac's predicted particles should. The positron had been discovered. What had begun as an abstract feature of an equation turned out to be a real component of the universe. This discovery carried deep implications for the nature of the vacuum. If particles and antiparticles can exist as symmetrical partners, then the vacuum itself may contain the potential for both. In the quantum picture of reality, empty space is not simply the absence of particles. Instead, it resembles a balanced landscape where pairs of particles can emerge together. When a fluctuation of energy appears in the vacuum, it often produces a particle and its antiparticle at the same moment. The pair emerges from the vacuum together, exists for a fleeting instant, and then annihilates again. Matter and antimatter appear side by side like reflections in a mirror. This symmetry suggests that the vacuum contains a deep underlying balance. For every type of particle that exists in the universe, there may be an antiparticle partner. The vacuum does not prefer one over the other. It simply allows them to arise in pairs. Physicists sometimes describe this idea as a kind of hidden symmetry within the structure of reality. Imagine a perfectly calm surface of water. If a small ripple forms on the surface, the wave rises upward while a corresponding dip forms beside it. The motion occurs in balanced pairs, crest and trough. In a similar way, Fluctuations in the quantum vacuum often produce pairs of particles with opposite properties. The vacuum remains balanced overall. Nothing becomes something but only briefly and only in pairs. This delicate symmetry hints at something remarkable. The vacuum is not merely empty space. It is a framework filled with possibilities, a background structure from which particles can momentarily emerge. In this picture, the universe begins to resemble a vast ocean whose surface is constantly trembling with microscopic waves. Most of those waves disappear almost instantly, but under certain conditions a fluctuation might grow larger, and when that happens, the brief appearance of particles may become something more lasting. Understanding how such fluctuations behave would eventually lead physicists toward an even deeper theory, one that describes the vacuum not just as a place where particles appear, but as the foundation from which all particles arise. That theory is known as quantum field theory, and it transforms the meaning of empty space once again. By the time antimatter had been discovered, physicists were beginning to notice a deeper pattern hiding beneath the behavior of particles. Electrons, positrons, photons, and other particles all appeared in experiments as tiny localized objects. They could be detected by instruments. They left tracks in detectors. They collided and scattered like minuscule billiard balls. But the mathematics describing them suggested something stranger. According to the emerging framework of modern physics, particles may not be the most fundamental elements of reality. Instead, something even more basic lies beneath them. That deeper layer is known as a field. To understand what a field is, it helps to imagine something familiar. Consider the air in a quiet room. Even when the room feels calm and still, the air fills every corner. It exists everywhere in the space around you. If a sound is made, the air vibrates slightly, carrying waves across the room. The sound is not a separate object travelling through the air. It is a pattern of motion within the air itself. Physicists began to realize that something similar might be true for particles. Instead of imagining particles as tiny solid objects moving through empty space, they began imagining the universe as filled with invisible fields. Each type of particle corresponds to its own field that extends throughout all of space. There is an electron field, a photon field associated with light, fields connected to quarks, neutrinos, and many other particles discovered over time. These fields are present everywhere. Even in regions of space where no particles are observed, the fields remain. The vacuum, in this picture, is not the absence of everything. It is simply the calmest possible state of all these fields. Imagine once again the surface of a lake. If the water is perfectly calm, the surface appears smooth and undisturbed. But the lake itself is still there. The water fills the entire basin, even when no waves are visible. If a small disturbance occurs, a ripple travels across the surface. The ripple is not a separate object moving across the lake. It is simply a pattern of motion in the water. Quantum field theory suggests that particles behave in a similar way. A particle is like a ripple in its corresponding field. When the electron field vibrates in a particular way, we observe that vibration as an electron. When the photon field vibrates, we observe light. The particles detected in experiments are not isolated pieces of matter floating through emptiness. They are localized excitations of fields that already exist everywhere in space. This idea transforms the meaning of the vacuum once again. Empty space is not empty. It is filled with fields that extend throughout the universe. Even when the fields are perfectly calm, they still possess a small amount of background energy. Physicists call this the vacuum energy. The vacuum represents the lowest possible energy state of all the fields combined. But lowest does not mean zero. Because of the quantum uncertainty we discussed earlier, the fields can never remain perfectly still. Even in their calmest state, tiny fluctuations ripple through them. These fluctuations are the same processes that produce virtual particle pairs. The fields momentarily rise and fall, creating small disturbances that appear as particles before settling back into the vacuum. In this view, the quantum vacuum resembles a vast ocean of invisible fields gently trembling beneath the surface of reality. Particles are not permanent objects. They are temporary patterns emerging from deeper structures. This perspective also explains why different types of particles behave so consistently. Every electron in the universe possesses exactly the same mass and charge. Electrons do not vary from one place to another. They are identical because each one represents the same vibration of the same underlying field. Just as every ripple in a lake follows the same laws of water motion, every electron follows the same rules of the electron field. Quantum field theory therefore replaces the idea of a universe built from tiny solid objects. Instead, the universe becomes a tapestry of interacting fields. Matter, radiation, and energy all arise from patterns within this invisible fabric. The vacuum, which once seemed like an empty stage, becomes the quiet ground state of these fields. It is the calm background from which all particles emerge, and this realization carries an astonishing implication. If fields fill all of space, and if the vacuum is simply the calmer state of those fields, then the vacuum itself contains the ingredients necessary to produce particles whenever energy disturbs it. The universe does not require matter to exist first. It only requires the fields. From these fields, particles can arise. In a sense, the vacuum is not a void. It is a potential, a silent landscape containing the possibility of matter, energy, and structure. For most of the universe's history, this potential remains subtle, revealing itself only through tiny fluctuations. But in the earliest moments of cosmic history, something extraordinary may have happened. Small fluctuations in these fields could have grown rapidly. Ripples in the vacuum may have expanded and shaped the large-scale structure of the cosmos. Galaxies, clusters of matter, and vast cosmic patterns might trace their origins back to tiny quantum fluctuations in the vacuum itself. To understand how this might occur, we must turn our attention to the earliest moments of the universe, a time when space itself was expanding at an astonishing rate. By the time physicists began to understand the quantum vacuum as a sea of invisible fields, a remarkable possibility started to emerge. If fluctuations can occur naturally within those fields, then the vacuum is never perfectly quiet. Even when the universe appears calm and empty, microscopic ripples of energy may briefly appear and disappear. For most of cosmic history, these fluctuations remain extremely small. They flicker for an instant and vanish again. But there was a moment, very early in the history of the universe, when the conditions of space were dramatically different. To understand that moment, imagine the universe not as the enormous cosmos we see today, but as something far smaller. In its earlier stages, the entire observable universe may have been compressed into a region far tinier than an atom. The temperature was unimaginably high. Energy filled every corner of space, and the structure of the vacuum itself may have been very different from what we observe today. Physicists believe that shortly after the universe began expanding, space experienced a brief period of extremely rapid growth. This idea is known as cosmic inflation. During inflation, space did not merely expand steadily. Instead, the fabric of space itself stretched outward at an astonishing rate. Distances doubled again and again in fractions of a second. Regions that were once microscopic suddenly became enormous. To picture this process, Imagine drawing tiny dots on the surface of a balloon. As the balloon inflates, the dots move farther apart from one another. But something else happens as well. Any small imperfections on the surface of the balloon become stretched and magnified. Tiny wrinkles grow larger. Minute variations become visible patterns. Inflation may have done something similar to the quantum fluctuations in the early vacuum. Before inflation began, the vacuum already contained the small flicker of energy we described earlier. These fluctuations were extremely tiny, far smaller than atoms. Under ordinary conditions, they would have remained microscopic forever. But inflation acted like a powerful magnifying process. As space expanded rapidly, the tiny fluctuations were stretched across enormous distances. Ripples that once existed only at subatomic scales became large enough to influence the distribution of matter across the universe. You can imagine it like ripples on the surface of water suddenly freezing into place while the lake expands outward. The pattern of the ripples becomes preserved. Later, as the universe continued evolving, these ripples in the density of matter began to influence how gravity pulled material together. Regions that were slightly denser attracted more matter. Over millions and billions of years, those denser regions grew into clouds of gas. Those clouds eventually formed the first stars. Groups of stars gathered into galaxies. Clusters of galaxies assembled into vast cosmic structures stretching across hundreds of millions of light years. In this way, the large-scale structure of the universe may trace its origins back to the tiny quantum fluctuations that once flickered inside the early vacuum. The galaxies we observe today, including the one that contains our own Sun, may ultimately be descendants of those microscopic ripples. Remarkably, astronomers have found evidence supporting this idea. When we observe the faint radiation left over from the early universe, known as the cosmic microwave background, we see subtle variations in temperature across the sky. These variations are extremely small, only a few parts in 100,000. Yet they reveal a pattern of slightly denser and slightly less dense regions in the young universe. The pattern matches the predictions of inflation remarkably well. It suggests that the seeds of cosmic structure were indeed planted by quantum fluctuations in the vacuum. In other words, the galaxies, stars, and planets of today may ultimately trace their origins to tiny fluctuations in what once appeared to be empty space. The quiet vacuum of the early universe contained small ripples of energy. Inflation stretched those ripples across cosmic distances. Gravity later amplified them into the structures we see across the night sky. The idea carries a strange beauty. Everything we see in the cosmos, every galaxy, every star, every planet, may have grown from faint quantum whispers that once flickered in the vacuum of space. The universe, in a sense, may have grown from the restless activity of nothing. Yet another mystery remains. If the vacuum naturally produces particles and antiparticles in balanced pairs, then the early universe should have contained equal amounts of matter and antimatter. But when astronomers observe the universe today, they find something curious. Almost everything we see is made of matter. Antimatter is extremely rare. Somehow, during the early history of the cosmos, a tiny imbalance appeared. For every billion pairs of matter and antimatter particles that annihilated each other, perhaps a single extra particle of matter remained. Those surviving particles eventually formed all the stars, planets, and living beings that exist today. Understanding how that imbalance arose is one of the deepest questions in modern physics. If the vacuum can produce particles in balanced pairs, and if the early universe was filled with enormous energy, then the beginning of the cosmos should have been a place where matter and antimatter appeared in equal amounts. According to the laws of physics as we understand them, every particle of matter has a mirror partner made of antimatter. Electrons have positrons. Protons have antiprotons. Many other particles discovered in modern physics also possess their corresponding antiparticles. When matter and antimatter meet, they annihilate each other. Both disappear, converting their mass into bursts of energy. In the early universe, when temperatures were extremely high and energy was abundant, particles and antiparticles should have been created constantly. Pairs would form, collide, and vanish again in flashes of energy. For a brief moment in cosmic history, the universe may have been filled with this continuous dance of creation and destruction, particles appearing, particles disappearing, matter and antimatter balancing each other perfectly. If that balance had remained exact, the story of the universe would have ended very quickly. As the cosmos expanded and cooled, matter and antimatter pairs would have continued to annihilate each other until nothing but radiation remained. No atoms, no stars, no galaxies, no planets, and certainly no living beings asking questions about the nature of nothingness. Yet the universe we observe today clearly did not follow that path. Matter exists everywhere. Every star, every planet, every cloud of gas in the cosmos appears to be made almost entirely of matter. Antimatter, by contrast, is extremely rare. Occasionally it appears in high-energy environments such as cosmic rays or particle accelerators, but large regions of antimatter do not seem to exist in the observable universe. Somehow, in the early moments of cosmic history, a tiny imbalance emerged. Physicists estimate that for roughly every billion pairs of matter and antimatter particles created in the early universe, there may have been one extra particle of matter. The rest annihilated each other, but that tiny surplus remained. Those surviving particles eventually combined to form the first atoms. Atoms gathered into gas clouds. Gas clouds collapsed under gravity to form stars. Stars produced heavier elements. Planets formed. And billions of years later, those same particles now form the atoms in your body and the stars above your head. Everything we see in the universe may trace its existence back to that tiny imbalance. Without it, the cosmos might have become an empty sea of radiation long before galaxies could form. Understanding how that imbalance arose remains one of the great mysteries of modern physics. Scientists refer to this puzzle as the problem of matter-antimatter symmetry. Several ideas have been proposed to explain it. Some theories suggest that certain processes in the early universe slightly favoured the production of matter over antimatter. Others suggest that the laws of physics themselves may treat matter and antimatter in subtly different ways under particular conditions. Experiments have revealed small differences in the behaviour of certain particles and their antiparticles. These differences are known as symmetry violations. In most everyday situations, the laws of physics treat matter and antimatter almost identically, but under very specific circumstances, tiny asymmetries appear. Imagine flipping a perfectly balanced coin. If the coin is truly fair, heads and tails should appear with equal probability. But suppose that after billions of flips, you notice that heads appear slightly more often than tails. The difference might be extremely small, perhaps one extra head in every billion flips. Yet over a very large number of flips, the imbalance would gradually become noticeable. Something similar may have happened in the early universe. The laws of physics may contain tiny biases that slightly favoured matter over antimatter during certain interactions. Over time, those small differences could have allowed a tiny surplus of matter to survive. Another way to picture this idea is to imagine a vast crowd leaving a stadium through two identical exits. If both exits allow people to leave at exactly the same rate, the crowd will empty evenly. But if one exit allows even a slightly faster flow of people, more individuals will eventually leave through that path. After enough time, the difference becomes significant. In the early universe, the interactions between particles may have contained a similarly small preference. The difference was almost imperceptible, yet it was enough to change the destiny of the cosmos. Modern particle accelerators continue searching for clues to this mystery. Experiments at facilities such as the Large Hadron Collider study the behavior of particles and antiparticles with incredible precision. Scientists hope that these experiments may reveal deeper asymmetries hidden within the laws of nature. Such discoveries could explain why matter survived while antimatter almost entirely vanished. The question touches something profound about the nature of reality. The universe we inhabit may exist because the laws of physics are not perfectly symmetrical. A tiny imbalance, perhaps 1 part in a billion, allowed matter to survive the fiery chaos of the early cosmos. From that small difference grew the vast structure of galaxies, stars, and planets. In the story of the universe, the difference between something and nothing may have depended on an almost imperceptible tilt in the balance between matter and antimatter. After exploring the strange behavior of the quantum vacuum, a natural question begins to emerge. If empty space contains energy, and if fluctuations within that space can briefly produce particles, then perhaps the vacuum itself possesses the ingredients needed to create something larger, perhaps even something as large as a universe. At first, the idea may sound almost poetic. But over the past several decades, physicists have seriously explored the possibility that the universe might have emerged from a quantum vacuum. To understand why this idea is considered plausible, it helps to recall what we mean by the vacuum. In classical thinking, empty space meant the complete absence of matter and energy. But modern physics paints a different picture. The vacuum is the lowest energy state of a universe filled with quantum fields. Those fields extend everywhere. Even when they appear calm, they contain small fluctuations and background energy. The vacuum, therefore, is not nothing in the philosophical sense. It is a physical state governed by the laws of quantum mechanics. One of the most intriguing features of this state is that it can allow spontaneous events to occur. We've already seen that tiny burst of energy can appear briefly within the vacuum, producing pairs of particles that quickly annihilate again. These events are incredibly small and short-lived, but they reveal an important principle. Quantum processes do not always require an external cause in the classical sense. Sometimes the laws of nature allow certain events to occur spontaneously as part of the statistical behavior of quantum systems. This insight has led some physicists to consider a remarkable possibility. If small fluctuations can appear within the vacuum, could a much larger fluctuation also occur? Could a sufficiently large fluctuation produce a region of space that begins expanding on its own? In certain models of cosmology, the answer may be yes. The idea rests partly on the unusual properties of gravity. Unlike most forces in physics, gravity can contribute negative energy to a system. This concept may seem unfamiliar, but it has a simple, intuitive picture. Imagine lifting a stone upward away from the Earth. As the stone rises, it gains what we call gravitational potential energy, but the Earth-stone system itself becomes slightly less tightly bound by gravity. In physics, we often describe this change by saying that gravitational interactions contribute negative energy relative to a chosen reference level. When cosmologists examine the total energy of the universe, they sometimes find something surprising. The positive energy associated with matter and radiation may be balanced by the negative energy associated with gravity. If those two contributions cancel each other, the total energy of the universe could be extremely close to zero. In such a situation, creating a universe would not require an enormous net supply of energy. Instead, the positive and negative contributions could balance each other. The idea is sometimes compared to digging a hole in the ground and piling the dirt beside it. The hole represents negative depth, while the pile represents positive height. If you measure the total amount of Earth relative to the original flat surface, the two changes can cancel each other. The ground has been reshaped, but the total amount of material remains the same. In a similar way, the creation of a universe might involve both positive and negative contributions of energy that balance overall. Quantum cosmology explores models in which a small region of space could spontaneously appear as a fluctuation of the vacuum. If that region possessed the right properties, it might begin expanding rapidly through a process similar to cosmic inflation. Once inflation begins, the expansion of space can continue, producing a universe that grows enormously larger than the initial fluctuation. The original quantum event might have been extremely tiny, yet through expansion, it could evolve into a cosmos containing billions of galaxies. Physicists such as Alexander Vilenkin and others have studied mathematical models describing how such a process might occur. These models suggest that the birth of a universe could arise naturally within the framework of quantum theory. Of course, these ideas remain areas of active research. They are not yet confirmed in the same way that the Lamb shift or the Casimir effect has been confirmed. But they illustrate how modern physics approaches the question of cosmic origins. Instead of asking whether something can arise from absolute philosophical nothingness, scientists investigate the behavior of the physical vacuum, a state governed by quantum fields and the laws of nature. Within that framework, the emergence of a universe becomes a question of probability, fluctuations, and the dynamics of space itself. In this view, the vacuum is not merely the background of the universe, it may be the stage from which universes can emerge, and that possibility leads us back to the original question that began this journey. When we ask what nothing really is, we may discover that the answer is far richer than the word suggests. At the beginning of this journey, we asked a question that seems simple at first. What is nothing? It is a question that philosophers have puzzled over for thousands of years. The idea of absolute emptiness appears straightforward when we say the word, yet the moment we try to imagine it clearly, the concept becomes strangely difficult. Even picturing an empty room does not truly represent nothing. The room still contains air, light, and space itself. If we remove the air, we're left with a vacuum. But as we have seen, even the vacuum is not truly empty. Throughout history, our understanding of nothing has changed again and again. Ancient philosophers such as Aristotle believed that nature could not tolerate a vacuum. The idea of empty space seemed impossible to them. For centuries, that belief shaped the way people thought about the universe. Later, experiments by scientists such as Torricelli and Pascal demonstrated that empty regions of space could indeed exist. The vacuum was real. For a time, physicists imagined that even this vacuum must be filled with something invisible, the mysterious ether through which light waves travelled. But careful experiments eventually showed that the ether did not exist. Light required no hidden medium. Space appeared to be truly empty after all. Then quantum physics arrived and quietly overturned that conclusion once again. According to quantum theory, empty space cannot remain perfectly still. The uncertainty inherent in the laws of nature allows small fluctuations of energy to appear and vanish within the vacuum. From those fluctuations, particle-antiparticle pairs may briefly emerge. Even when every particle has been removed from a region of space, the vacuum remains alive with microscopic activity. The quiet void becomes a restless sea. Modern physics has taken the idea even further. Instead of imagining particles as the fundamental building blocks of reality, physicists now describe the universe as filled with quantum fields. These fields exist everywhere. Particles appear as small vibrations within them, much like ripples travelling across the surface of water. The vacuum is simply the calmest possible state of these fields. Yet even in this calm state, tiny fluctuations remain. Those fluctuations leave measurable fingerprints, are seen in experiments such as the Lamb shift and the Casimir effect. They also may have played a role in shaping the large-scale structure of the universe. Tiny ripples in the early vacuum could have been stretched by cosmic inflation, eventually becoming the seeds of galaxies and clusters of stars. And in some theories of quantum cosmology, the vacuum itself may even allow entire universes to emerge as rare but possible fluctuations. The idea is both subtle and profound. When physicists speak about nothing, they are not referring to the philosophical absence of everything. Instead, they are describing the lowest energy state of a universe filled with fields governed by the laws of quantum physics. This vacuum is quiet, but not empty. It contains structure, it contains energy, and it contains the potential for particles, forces, and even cosmic structure to arise. The word nothing, in science, turns out to describe something far richer than we might have imagined. If we look out into the night sky, we see vast regions of darkness between the stars. Those spaces once seemed like empty voids. But modern physics suggests that even those silent regions are filled with invisible fields and faint fluctuations of energy. The universe is not a collection of objects floating in nothingness. It is a dynamic tapestry woven from fields, energy, and space itself. The vacuum is part of that tapestry, a quiet background from which the patterns of matter and light emerge. In this sense, the question we began with, how something could arise from nothing, may contain a hidden misunderstanding. The vacuum is not, truly nothing, is a physical state governed by the laws of nature. Within that state, fluctuations occur, particles appear and disappear, and under the right conditions, the seeds of cosmic structure can grow. From the calmest background of reality, complexity emerges. Galaxies form, stars ignite, planets circle their suns, and on at least one small planet, conscious beings begin asking questions about the universe itself. The journey from nothing to everything may not be a leap across an impossible gap. It may be a gradual unfolding of patterns already hidden within the structure of the vacuum, and so the idea of nothing becomes less like an empty void and more like a quiet foundation. A silent stage upon which the drama of the universe slowly unfolds. And now, as our exploration gently comes to an end, you might find yourself thinking about the spaces between things, the darkness between stars, the quiet between breaths, the stillness that surrounds every moment. Those spaces are not empty. They are part of the same vast universe that produced galaxies, atoms, and the thoughts passing through your mind right now. Nothing, it turns out, may be one of the most interesting things in the cosmos. And so, we've reached the end of tonight's exploration. Whether your eyes are still open, or you're already floating somewhere between waking and dreaming, thank you for being part of this little journey. If you'd like to join me again for more gentle wanderings, you're always welcome to subscribe or share this with someone who could use a peaceful pause. Time has a way of slipping through our fingers, but here, in this quiet moment, it's just you and the soft hush of rest. Sleep peacefully, wherever and whenever you may be.